talking. Hey everyone. So today we are going to be talking about our project on associated learning versus back propagation in vision transformers. This is, pretty interesting stuff because, we are basically challenging one of the most fundamental ways that we train our neural networks today. So let me start with some context here. For decades now, right, basically every neural network has been trained using something called back propagation and back propagation or BP as well as we call it. It's essentially this algorithm where you run your data forward through the network. You calculate how wrong your predictions are, and then you propagate that error backward through every single layer. Mm. It uses something called the chain rule from calculus, and it updates every parameter based on how much it contributed to the final error. Now, BP works really well. Don't get me wrong. It's the reason we have all these amazing AI models today. But it has some pretty significant limitations that we should talk about. First off, memory usage is huge. Because you see, BP needs to store all these intermediate activations during the forward pass so it can use them later during the backward pass. And when you are dealing with massive transformer models, this memory requirement just explodes, right? Second thing is the layers are tightly coupled together. What I mean by that is every layer depends on gradients flowing backward from the layers above. So this makes it really hard to parallelize training or do distributed learning efficiently. And third, BP requires these exact gradient signals. If anything disrupts the flow, like noise on certain types of layers, the whole learning process basically breaks down. So, because of these limitations, researchers have been looking for alternatives. And that brings us to the associated learning or AL, which was proposed by Wu and colleagues at ICLR 2022. Now, AL is fundamentally different from backpropagation because instead of propagating gradients through the entire network, it trains each layer independently using local objectives. Here's how it works, okay? So each layer gets four small modules attached to it. There's the main forward transformation. That's just your regular layer. Then there's a bridge module that maps that layer's output into a shared latent space. Then an encoder that maps the target signals into the same space. And finally, there's a decoder that reconstructs the previous layer's target signal. During training, you do a forward pass through all the layers, and this is the key. You detach the activations at each layer to prevent gradients from flowing between layers. Then each layer gets trained independently by aligning its representation with its encoded target and reconstructing the previous target. So basically, no gradients flow across layers at all. Each layer has its own local learning objective. The motivation behind AL is pretty compelling, actually. It should reduce memory requirements because you don't need to store the full computational graph. It decouples layers, which could enable more flexible training. And it's arguably more biologically plausible than backprop, which is kind of cool from a neuroscience perspective. Now, previous work has that AL can match or approach backprop performance on CNNs and some language models. But here's the thing: nobody has really tested it on vision transformers yet, especially not with hardware metrics like energy consumption and flops. And that's exactly what we set out to do in this project. We wanted to understand not just if AL works on vision transformers, but whether it actually delivers practical benefits in terms of computational efficiency. So that's the setup.
Let me talk about how we actually did this study and what our experimental setup looked like. First, we needed to choose our data sets, right? So we picked two standard vision benchmarks to keep things, reasonable and focused. So first thing is Fashion MNIST. It's a pretty simple data set with 28 by 28 grayscale images of clothing items across 10 classes. It is kind of easy. So we used it as a sanity check, basically to make sure our associate learning implementation was working correctly. And the second data set is CIFAR-10. This one's more challenging. It has 32 by 32 RGB images across 10 classes. The images are more complex and diversity. It's generally considered a more realistic test bed for vision models. For both datasets, we only use standard normalization and basic augmentation, like random crops and horizontal flips. Um, Now let's talk about the model architecture. We used a lightweight vision transformer for this study. So vision transformers, they're different from traditional CNNs. Instead of convolutions, they split images into patches and treat them as tokens, kind of like words in a sentence. Um, each patch gets embedded into a high dimensional vector. You add a positional embeddings to give a spatial structure. Then you stack multiple transformer encoder blocks with self-attention and MLBs. For our experiments, the specific architecture is what we used is 4 by 4 patch size for CIFAR-10 and 7 by 7 for FashionMNIST. The embedding dimension was 192 for CIFAR and 128 for FashionMNIST. We had uh, we had 4 transformer blocks in total and 8 attention heads. The MLP and MLP hidden size was 768 for CIFAR and 512 for FashionMNIST. For the baseline model, with propagation, the architecture ends with a standard classification head that maps the class token to class logics. For the associate learning version, though we had to augment each transformer block with those four additional modules I mentioned earlier: the forward map, the target encoder, the decoder, and the bridge. The first layer has special dimensions because it needs a map from class levels, but deeper layers all use a fixed latent dimension of 26. Okay. For okay, so the training setup, we trained both backpropagation and associate learning for 30 epochs with identical hyperparameters to keep things fair. We used the Adam optimizer with a learning rate of 3 times 10 to the it's for C for 10 and 1 times 10 to minus 3 for fashionableness. Batch size was 128 across all experiments. For backpropagation, the loss function was just standard cross entropy for associate learning. We used the two local losses exactly as defined in the original paper. The association loss that aligns representations with targets, and the autoencoder loss that reconstructs the previous target signal. Now, implementing the associate learning correctly was actually like really important and a bit tricky. We had to make sure that during the forward pass, all intermediate states were explicitly detached to prevent gradients from flowing between layers. Then, for each layer, we created a fresh computational graph using those detached inputs and trained the layer in complete isolation. We verified this was working correctly by inspecting gradients, checking tensor sheets, and running convergence tests on small examples before scaling up. Let me also tell about how metrics are evaluated because we want it to be really comprehensive here. We evaluated along two axes: statistical performance and hardware behavior. For statistical metrics, uh, we tracked top one accuracy, that's a primary metric. We also looked at convergence speed by plotting accuracy versus epoch curves. And for associate learning, specifically, we monitored the evolution of two local losses throughout training to make sure they were behaving as expected. As for coming for hardware metrics, and this is very important one. We measured flops using a profiling library, peak GPU memory using PyTorch's memory profiler, wall clock time per epoch averaged over multiple batches, and energy consumption using PyTorch power sampling interface. All these measurements were collected on the same GPU instance in Google Colab under identical conditions. This was super important because we wanted to ensure that any differences we saw were actually due to the training method, not and not variations in hardware or environmental factors. So that's our methodology in a nutshell. We got two data sets clearly implemented VAT with both propagation and associated learning, and a comprehensive set of metrics to evaluate both accuracy and computational efficiency. Now, let me hand over the next part to my friend.
Okay, so this is where things get really interesting because the results actually tell a pretty nuanced story about about when AL works and when it doesn't. Let me start with FashionMNIST because the results there were actually quite encouraging. So if you look at the training accuracy curves, both backpropagation and associated learning show really smooth curves, and they have consistent improvement throughout the 30 epochs that we trained for. So like there is no weird instability or divergence or anything. Both methods just steadily learn, which is great. This suggests that AL is definitely capable of learning high quality representations even without full backpropagation. And the gradient stopping mechanism is not breaking anything. Now, when we look at test accuracy, which is obviously what we really care about, both BP and AL generalize similarly well, at least for FashionMNIST. So the curves stay pretty close throughout training with just small fluctuations, which is normal for FashionMNIST. And interestingly, AL actually shows slightly faster early generalization between epochs 3 and 7, reaching around 88 to 89%. And BP catches up in the mid training region, and then in the later epochs both models kind of oscillate within the same band, and the final test accuracy is effectively identical at about 89% for both of them. So for FashionMNIST, AL is definitely competitive with backpropagation, and it even shows somewhat faster convergence early on, which is pretty cool. We also looked at behavior of AL's two internal losses, the association loss and the autoencoder loss. The association loss decreases steadily and smoothly, which confirms that the bridge-based alignment mechanism is working as intended. The autoencoder loss drops really dramatically by almost two orders of magnitude within the first few epochs, and then it stabilizes with small fluctuations. And this is exactly what you'd expect because it's reconstructing progressively smaller residual errors as we go. And now here is the thing about FashionMNIST. It's a relatively simple dataset. The images are grayscale and the features are not super complex, and you don't need deep hierarchical representations to do well. So AL's layer-wise objectives are basically good enough here. And the lack of full gradient flow is not a bottleneck here because the learning signals are simple and local learning works just fine. But, and this is a big but, CIFAR-10 paints a very different picture here. On CIFAR-10, BP performs normally, reaching about 76% accuracy in 30 epochs. But what about AL? AL only reaches 64% here, and that's a 12% uh, point gap, and it's very large and persistent throughout the training. Like it never closes even after 30 epochs. Maybe after 30 epochs, if we continue training, it might close, but we did not train it for that many epochs. And this is a pretty significant limitation of the current AL algorithm. And CIFAR-10 has more complex visual patterns, so it has more color information, higher frequency details, and it requires more sophisticated hierarchical feature learning. And it seems that like AL's layer-wise targets just are not rich enough to capture all that complexity. Without full gradient flow, the deeper layers are not getting the right learning signals, so they need to build really good representations. Now let's talk about the hardware side of the things, which is honestly a bit surprising. We originally expected AL to be cheaper computationally, at least, because it does not do backpropagation through the entire network, right? But in practice, that's not what we saw. For FashionMNIST, back BP took about 12, 1200 joules of energy per epoch, and each epoch took about 24 seconds on average to complete. AL, on the other hand, took about 1600 joules per epoch and 25 seconds per epoch. So AL is actually slightly more expensive. For CIFAR-10, the gap is even more noticeable here. BP averaged 41 seconds per epoch, but AL took 45 seconds. That's about 10 to 12% slower. Peak GPU memory usage was also slightly higher for AL. It was 810 megabytes, and for backpropagation it was 250 for Cypher 10, and it was 210 on FashionMNIST. This extra memory is probably because AL needs to maintain separate optimizers and those auxiliary autoencoder modules for every single layer. And here is the kicker: energy consumption was significantly higher for AL. We saw 2700 to 2850 joules per epoch for CIFAR-10 and 1500 to 1750 joules per epoch for FashionMNIST. That's a 25 to 30% increase over backpropagation. So not only is AL slower, it's also more energy hungry. Now, why is this happening? Well, the per layer forward passes, the target generation, and all those auxiliary autoencoders add enough overhead that AL actually ends up being less efficient than backpropagation, at least in this implementation, in our implementation, and for this dataset, CIFAR-10. And the theoretical benefits of not doing full backprop just don't materialize in practice because of all the extra machinery that AL requires. That said, it's worth noting that this overhead might become negligible if you are working with really large architectures. Like if you have massive model with hundreds of layers, the relative overhead might not matter as much. But for the lightweight VITs we tested, it's definitely a problem. So to summarize the results, on simple datasets like FashionMNIST, AL matches BP in terms of accuracy and even shows faster early convergence. But on complex datasets like CIFAR-10, there's a persistent and significant accuracy gap. And across both datasets, AL is actually slower and more energy hungry than BP in its current form. So let me hand it over to wrap things up.
Yeah, so let me conclude all this together and talk about what these results actually mean and the limitations of our study and what we think this could go in future. So first, let's be honest about what we found. The trade-offs between backpropagation and associated learning are pretty clear at this point. On Fashion MNIST, AL behaves almost exactly like BP in terms of generalization. The curves track each other closely, the final accuracy gap is basically negligible, and everything looks good. This tells us that on simpler datasets with low visual complexity, AL's layer-wise targets are sufficient for stable learning. The mechanism fundamentally works, which is encouraging. But Cypher 10 really exposes the weakness of our current AL formulation. That accuracy gap 12% points grow steadily and never closes, at least not in the 30 epochs we tested. BP reaches about 76% while AL stalls near 64%, and that's a large and persistent difference. This points to a real limitation in how well AL handles high frequency visual details and deeper hierarchical features. Without full gradient flow, the layers aren't just coordinating well enough to build the complex representations needed for harder visual tasks. And then there's the hardware side, which was honestly surprising to us. We expected AL to be cheaper because it doesn't do backpropagation through the entire network. But in practice, the per layer forward passes, the target generation, and all those auxiliary auto encoders add enough overhead that AL ends up being slower and more energy hungry. These increases aren't massive. We are talking 10 to 30%, but they are consistent across the board datasets. Now, to be fair, this overhead might become less significant if you are working with really large architectures. Like, you have a model with 100 layers. The relative cost of those small auxiliary modules might not matter much. But for the models we tested, it's definitely a practical concern. Let me talk about the limitations of our work because there are definitely things we didn't cover. First, our real implementation relies heavily on the hand designed layer wise target mappings, the encoder and decoder modules. In our setup, these are simple MLPs, and it's not obvious whether they are expressive enough for deeper models or harder datasets. There might be a better architectural choice and could improve AL's performance. Second, AL requires the maintaining additional modules for every layer and running multiple smaller forward passes during training. This adds memory and runtime overhead, while design is conceptually parallel friendly. In most operations, still run sequentially. So the theoretical efficiency benefits just don't materialize with current hardware and software. Third, our evaluation is limited to relatively shallow VITs, vision transformers, with small patch size on medium scale datasets. We don't know how well the AL scales to larger networks, bigger data sets like ImageNet or modern architectures. We also didn't incorporate techniques like advanced data augmentation, knowledge distillation, or sophisticated optimization strategies that might help close the accuracy gap. And finally, the performance degradation on CIFAR-10 compared to backpropagation is pretty clear, which suggests that AL might not be robust to complex high variance natural images without some serious improvements to how targets are generated and propagated. So, what's the key takeaway here? Well, this work compared backpropagation with associated learning in a clean controlled setting using a vision transformer on two standard datasets. The results show that AL can match BP on simple datasets, but it falls behind once visual complexity increases. Even though AL avoids full backpropagation, the extra components it introduces create their own computational overhead. In its current form, AL is not competitive with BP in either accuracy or efficiency for moderate difficulty image classification. But I want to emphasize this. AL is still an interesting idea with real potential. The fact that it performs reasonably well on fashion MNIST means the core mechanism works. The local learning objectives are well conditioned. They converge reliably, and there's definitely room to improve things. Better target generation, more stable training dynamics, reducing the overhead through better implementation. These are all the areas where the future work could make a big difference. You could also imagine hybrid approaches that combine the best of the both worlds. Maybe you can use a associated learning for some layers and then backpropagation for the others. Or maybe you use AL during the parts of training and then fine tune with the backpropagation. There are lots of possibilities to explore. But right now, based on our experiments, backpropagation remains a stronger and more reliable option. It's more accurate, it's actually more efficient in practice, and it's method that's been highly tested on millions of models. But associated learning also has promise, but it needs more development before it can compete in real world settings. So, yeah, that's our project. We hope this gives you a clearer picture of how associated learning compares to backpropagation on vision transformers, both in terms of accuracy and hardware efficiency. Yeah, thank you.